In this video, we're going to run through the list of reactions that we're going to discuss for aldehydes and ketones, and then also talk about just the general mechanism for many of these reactions because they are all classified as nucleophilic addition reactions to carbonyl groups. So here are all the reactions that we will cover for aldehydes and ketones. We have oxidation, which is actually review. We have already done oxidation of these groups, but I will review those quickly. Then the big thing for this section are these nucleophilic addition reactions. We've got a number of them to talk about. The mechanism for these reactions is very similar, at least as far as the basic steps go. Depending on what you're adding, the kind of fine details might be a little bit different. So we can do hydration, which is essentially addition of water. And what we're going to get from this typically is a diol. So we're going to add 2 alcohol groups. Cyanohydrid formation, what we are adding is HCN. So you'll be adding a cyano group. Hydride reagents, which would lead to reductions, as well as the Grignard reactions, both of these are going to produce alcohols. And those reactions are also review. We've got imine and enamine. We've got some autocorrect issues here. This is one word. So imine and enamine formation. Here, depending on what reagent you're using, both of them are going to be amines, but whether it's primary or secondary will determine if you get imine or enamine. Wolff-Kishner reaction, what you get from this is an alkane. Acetal formation, you're going to make an acetal. And then the Wittig reaction, what we are going to produce is an alkene with added carbons to the original starting material. So before we go into each of those reactions in great detail, I want to give you some of the general mechanism concepts that you want to consider whenever you're doing any of these nucleophilic addition reactions. So first thing to think about, we're going to always be starting with a carbonyl, whether it's a ketone or an aldehyde. Now remember, these carbonyls do have resonance structures. Obviously the neutral is going to be your primary structure. However, this is a valid resonance structure. And what this shows is that this carbon is electrophilic. It does have some partial positive charge within the overall average structure. So we have an electrophilic carbon. If I can write. So the nucleophilic addition means we're going to have some other nucleophile typically come in and attack that carbon as the electrophile. A few other things to note. Aldehydes are typically more reactive than ketones. And that's for a couple of reasons. One is if you're using a ketone, these R groups add steric. So if your nucleophile is trying to come in and attack, if those R groups are big and bulky, and there's 2 of them, it's going to be more difficult for that nucleophile to get into that space. Also, if we think about this second resonance structure here, we have a carbocation. So a secondary carbocation here with 2 R groups versus if it was an aldehyde and therefore primary and only 1 R group, that primary carbocation is going to be more reactive than the secondary. So those are a few things to consider. As far as the general steps, there's a couple of different ways these reactions can go. So again, if we start with our carbonyl, one typical pattern is if we have a negative nucleophile, That's going to attack that electrophilic carbon directly and kick the pi electrons in the double bond up. We are always going to form a tetrahedral intermediate, meaning 4 bonds to that carbon. So here's that tetrahedral intermediate. This is usually then followed with some kind of acidic workup, or your nucleophile solvent has an acidic proton that can be removed. And so the negative charged oxygen, those electrons are going to come grab a hydrogen, kick off the other half of the acid, and you now have your product. So depending on what that nucleophile was, and in this example, we are actually ending up with some kind of alcohol. Another common option is for your nucleophile to be neutral. If that comes in and attacks the carbonyl electrophilic carbon there, again, we're going to get a tetrahedral intermediate. In this case, my nucleophile that's added now has a positive charge. Here, what commonly happens is something called a tautomerization or a proton transfer. So the hydrogen, one of the hydrogens on the nucleophile is going to transfer up to the oxygen. A lot of times this is kind of shortcutted in mechanism. You can write tautomerization. You can write kind of a plus minus that hydrogen ion because it's being removed and then added to another location. So once I transfer that hydrogen, I have a structure something like this. And then again, depending on what the nucleophile is, what the solvent is, this is where those nitty-gritty details kind of depend on the actual reaction. Usually what ends up happening is you're going to, again, protonate that alcohol group. But this time, once you protonate it again, you're going to be losing water. You're creating water as a leaving group. And then you're usually forming a double bond, not a nitrogen, this is nucleophile, excuse me, to whatever your nucleophile was. And we'll see several reactions that happen in that type of format. Okay. So again, our electrophilic position is the carbon of the carbonyl. We've got 2 options with a nucleophile. It could be either negatively charged or neutral. And then the third thing that we want to consider when doing these reactions is whether it's done in acidic or basic conditions. Okay, so if it is done in acidic conditions, the first thing that's going to be done is you're going to protonate the oxygen of the carbonyl. All right, so that oxygen has lone pairs, and if you have an acid, that's going to typically be the first step. And the reason for that is now when you draw the resonance structure of the protonated carbonyl, that oxygen is neutral. We only have that single charge rather than the double split charge that we saw earlier in the resonance structure. So this is just increasing the reactivity of that carbonyl. If it's done in basic conditions, you are going to be protonating later. And the steps that I showed you just above, we were always protonating later. And then your conjugate base that you're going to form will typically be negative. because once you remove that hydrogen, the conjugate base becomes negative. A few other things to consider with the acidic conditions. You're never going to have OH leave, so it's never going to be a leaving group if you're in acidic conditions. And if there's a charge anywhere, it's going to typically be positive. And this isn't an always statement, but if you're in acidic conditions and you have a formal charge, you're typically looking at positive. If you're working in basic conditions, formal charges are typically negative. So again, these are just some general ideas for the nucleophilic addition reaction mechanisms. Each reaction is going to have its own details to consider, but you always want to consider these main points.